Hey guys, what's up? Eddie Yahoo here with KissAnalog.com. Today we're back here at the Class A amplifier, 20 watt Class A amplifier. And what we're going to do is we're going to look, today what we're going to do is we're going to look at some waveforms. We're going to see when we're selecting our capacitor and our transformer and we want to come up with, the criteria for the design. Is it a worst case scenario at 20 kilohertz or 20 hertz? So we want to know that so that we can size the capacitors appropriately, right? And also we can decide on one of these two transformers here. All right, so let's bring the camera over and just take a look, and we're going to show you some waveforms. I think you're going to find them pretty interesting. I think they're pretty cool looking. One quick moment, let me pull up my board just to show you what we're going to be doing. My board. Just simple circuit here, just simplified. The power supply, transformer, rectifier, and the volt capacitors. Okay, I'm showing the transformer as a single primary. Really on this transformer, either one of these, there's two primaries. You stack them if you're doing 220. If you're 120 in the States, then you put them in parallel. So it looks like just one transformer winding. And then on the secondary you have two, and you stack those in either case. And you use the center for your ground or your reference, which is the center of your capacitors, same place, just tie that together. And then your top winding comes down here, your AC input. The bottom one comes over here to the other AC input of a bridge rectifier. Then the plus comes off here and the minus comes off here. So you get your plus and minus voltage rail. Okay, now I showed these dots. These two black dots next to these diodes, these two diodes would be on when you create this pulse and that pulse, and the red ones are on when you create this one and this one. When this is a plus up here, if I put the dots there, you'd have a dot here, dot, and this would be plus. The way the current would come this way, this would be minus, and the current would go that way. And then when this guy is minus, he goes this way. And this guy would be plus, and he goes that way. So you get your two reds. And then the voltage over here, if you put your scope here, which you could, because it's isolated, it's floating. If you did this, you would see 2 times V, and you can see these pulses. But if you took two probes and you put one here and one here, put the ground on in the center on both, in one case you get the negative ones, and the other one you get the positive ones. Yeah, that's just what it would look like, right? So, now here's the thing, is I'm showing how it charges and discharges. This blue line is discharging down here, hits the waveform as it comes up. The next time charges back up, so it's charging these volt capacitors that way, right? So you get this current from this start of that blue line to the end of that one, this pulse of current. Okay? Now, that's what I want to kind of show you. That's what's going to be cool. So let's come over here and take a look, see what that actually looks like. From say 20 kilohertz down to 20 hertz, okay? All right, guys, here's two of my mixed sig differential probes, and the current probe, and the Pentec differential probe. And there we are with our Unity generator. And I guess we're going to use the Hiraga voltmeter to take some readings. So, Class A amplifier. One of the differential probes here, we're going to be looking at the input signal, which coming from the Unity. On the output, we're going to be looking at the output voltage, of course, but we're also going to be looking at the voltage on the plus voltage rail of the amplifier, okay? And then I've got the Keithley 2015 THD meter right here, okay? So, looking at the input and the output, I'm using the current probe right here to look at the current coming from the lab power supply, which is a GW Instec GPC 3030. Okay, so that's the setup. Alright, so let's go ahead and turn on the power and look at the oscilloscope. Alright, channel 1 is going to be the output. Channel 2, you can see the input signal. These are differential probes. Channel 3 is the voltage rail. Okay, now to make it interesting, I got AC coupled, so we're going to just look at the ripple coming from the power supply. because the voltage is going to be well above, you know, the output signal, so that shouldn't be causing any clipping or anything. And then the current is also from the power supply. All right, so you'll hear power supply go on. All right, and I'll bring up the rails. And it takes just a moment for the power supply to fully come up. You can kind of see it was flatlined or is clipping a little bit. Okay, so the yellow one, output signal, blue one's input signal. Turn off the other two just for a moment so you can look at them. Okay, there's input and output. All right, and the voltages are down here, 12.63, so we're right about 20 watts and 377 millivolts coming in, roughly. So you can kind of calculate gain from that as well. Okay, let's turn on the voltage rail. Okay, that's the ripple from the voltage rail. You can see how it's just an inverse of the signal, because every time the signal draws power, then there's some ripple. Okay, now let me turn on the current. Okay, now that's the current. I'll turn off the voltage, output, input just for a moment. Okay, so that's the ripple on the power supply, the lab power supply coming in, the plus rail, and see how we're just coming off of the, what is this, 500 milliamps, so about 250 milliamps it almost comes down to, and there's a little bit of distortion there because it is probably charging, well, you know, it's charging caps, running circuitry and all that kind of stuff, but you can kind of see how it is in phase with the output. Let's turn that back on. There we go. I mean, it's slightly phase shifted, but it's pretty close. So as the output's drawing current, you're seeing a waveform from the power supply delivering the power. Okay, so now I'm at 31.6. My THD is about 0.03, and I think a lot of that's coming from the Unity, the generator. But okay, so I'm going to go ahead and drop the lab supply until I see it affect the THD. And what I find is I'm at 29 volts right now, and I'm still, you know, it's still well above. See, if you look at this 5 volts per division, we're 5, 10, 15, you know, what is that? Not even 20 volts, right? Say 18 volts peak. So, you know, putting out 28 volts, we still have 10 volts of headroom. But I do start seeing the distortion get affected when I'm dropping down to, okay, I'm at 28. Okay, right about just under 28, I see the THD just climb a little bit. It goes from 0.03 to about 0.035 or 7 or 8, and it's, you know, let me see, 0.04. Let's see how low we can go. Okay, it's right about 27.7. We're hitting about 0.04, so it's gone up just slightly. We don't see any clipping, right? I'll freeze this, turn off the power supply. All right, so what are we? We got 50 millivolts per division for the ripple from the DC supply. So it's, you know, it's 130 millivolts peak down here and maybe close to 100 millivolts peak on the top. So a very little ripple. You can see right here it says 77 millivolts RMS. So from this experiment, this is a good experiment with a lab supply. It gives us a baseline of how much voltage we need before we start affecting distortion. So it seems like if we stay above 28 volts, we're not going to affect distortion. All right, and so let's check the voltage on the op amp. Okay, come over this side. Okay, minus 21.29 and plus 21.79. So now I'll drop it down to 29 volts first, and let's see if we see any difference. It does affect it a little bit, right? It's coming down just ever so. I'm at 28 volts. Well, hold on a sec. Yeah, I'm at 28 volts now. So 21.5 to 21 point, you know, and it'll creep up to about 7.5. So it does take off maybe a a little bit of voltage on the op amp. Okay, 21.3. And that's when I have 31.6 volts, my max from my power supply. And now I'm down at 29 volts right there. And I'm at 28 volts now. So it looks like we do take off just a little bit of voltage off the op amp, dropping the voltage down to 28, but I didn't see the distortion being affected, so I think that's okay. Alright guys, let me just show you the AC power connection. We're going to hook up the transformer. So I've got the power cord right here. Okay, the neutral is this end here. It's going to go through the thermistor and then through the brown and gray. And I know I do this backwards from some people, but as long as you're consistent, you either call the dot your negatives or your positives, and you treat them the same on both sides, okay? So I'm putting my bottom of these two windings, I'm in the US, so I put them in parallel. If you're at 220, you'd put those in series. But so I'm using these really cool little connectors to put them together. So Wago, this is a different brand, I forget, but I think I have links down below for these. And then the hot comes in here and then connects up to the blue and purple right there through these connectors. And you can see the blue and purple are the dot ends. Okay guys, then on the secondary, we have our black as the top dot, and then we have our red and our orange in the center. So we're going to put those together right here for ground, okay? So that goes into the ground pin and to the speaker. And then the bottom's the yellow one. So here's our black and yellow one right here, okay? I'm just using this jumper right here. All this is so temporary just to test out this. And then they go down to the bridge rectifier. And the bridge rectifier looks like this. So you have an AC input on one corner. The opposite corner, you're going to have the other AC input. And then you got your plus. And on the opposite corner, you have your negative coming out. Okay, so it doesn't really matter which two pins on your AC they go to. This red and white wire coming from the transformer is going to go down to our AC. Okay, the center part's going right to the ground. So then the plus terminal off of this guy would go to the plus terminal up here, which is this one. And the minus terminal will come up and go to the minus terminal here. Okay, so and then all I'm doing is I've got these wires in, and then I've got the red and black one down here just clipped on with these two things. Like I said, this is super temporary just to test out this transformer, see if it's going to work for us. Now before I was coming in with the plus minus DC voltage, now I'm coming in with a pulsating DC waveform, right? Alright guys, so if I have 22 volts coming in off the transformer, and that's with 115 going into it, which we really have about 120, so the 115 is kind of on the low side. But if I take square root of 2 and multiply that, 1.4 times 22, we get 31.1 volts. So I should get plus minus 31.1 with not taking ripple in consideration. So yeah, we've got the caps here and these caps here. They're all bulk, but these big bulk caps are supplying the, they're going to try to smooth out the voltage for the power stage right here. Alright, just want to say I checked all my connections again very carefully, and then connected up the probes, and then I double checked everything. I got the distortion meter connected back up to the speaker output here, differential probes connected back up, and the current probe connected. So we should be looking, at the same kind of things we were looking at before. Okay, so let's go look at the scope. Okay, sorry about this probe right here. That is just kind of, it's probing my voltage rail. So I'm going to just check the voltage as it comes up. So what I do is I use a variac, I bring it up a few volts, and then I make sure the voltage at my supply rail is, the right polarity. I want to make sure I'm getting plus going to my plus supply and minus to my minus. So I'll move this in just a moment. But okay, so just to explain the setup change, what I did is channel 3 used to be AC coupled because we only cared about the ripple on the DC power supply. Now we have our AC voltage coming in. I've got this set to DC coupling 5 volts per channel. So 5, 10, 15, 20, 25. So it should be right up in here, you know. Okay, so I've got a signal going. You see the input signal. So we should see output signal on the yellow one. As soon as that happens, we should also see the current on the input supply. So let's check that. I'm looking at the Hioki. Make sure the voltage comes up right polarity. Okay, the kicked on. And yes, we look like we're right now I'm at 6 volts. So I'm going to check the minus to make sure it says minus 6 volts. And it does. So good. Alright, I'm going to trust it now. Well, kind of trust it. I've got my little plastic shield. I'm going to put over the board, the capacitors, in case anything does decide to blow up. It's not going to be in my face. Alright, let's bring up power again. Okay, there we go. Looks like everything's okay, so I'm going to bring it right up to 120, 115, somewhere in that area. And now look what we're looking at. What we got to do is, there's our 60 hertz, or really it's 120 hertz, right? It's doubled. So I'm going to freeze that just for a moment, drop the power so we can look at it a little closer, make sure. I mean, it looks fine to me, but so we've got our 60 hertz. I got the 1 kilohertz sine wave coming in, and look how, here, let me turn off things so we can just, okay, so the green wave forms the current, and the purple one's the output voltage on that rail. And isn't that interesting? The current should be just these big old bleeps, but instead, as the 1 kilohertz is pulling power, it's also pulling power off of this. So you get this 1 kilohertz kind of modulated waveform on top of it that you can see actually in the voltage waveform, the little steppy thing. So let's go ahead and bring up the voltage again. Well, and of course you can see the input signal. That's that one, and that's the output voltage. And you can see here, I'll spread it out so we're just looking at one of those. You can see every time we get a waveform, it's pulling current through that transformer. So we're getting, you know, instead of just getting a charge into the caps, we're getting this plus the current going to that signal. Now the other thing I guess we should note though, here, let's turn off that, is the voltage. See how far it drops? It goes 5, 10, 15, 20, 25, 30, you know, say 33 volts or something. And then it drops all the way down to, I mean, look how low it drops. So you got 5, 10, 15, 20, about 24 volts. So it looks like it's dropping below that 29 volt threshold that we kind of wanted to keep. All right, so let's bring up the voltage again. All right, now instead of 1 kilohertz, I'm going to go 10K, okay? Let's go up a little higher frequency. Okay, there's 10 kilohertz. I'm going to freeze that. We'll drop the power again. Let's just look at that for a moment. Here, I'll get rid of the output voltage. Okay, now we have a lot higher frequency, so it has a smaller effect on the current. Now the current, you see mostly the current just charging up the capacitors, and you see how they charge them up right here, and then right here we turn off and wait for the next cycle where the voltage has to be above the level of the you know, where it sags down. Now you can see where it sags down is the end of this cycle right here, and then right where it hits the low point here where this voltage is coming up, the input voltage, which we're not really looking at. Maybe I should have looked at that. But you can see where the current turns on. So right there is where that voltage sags. And again, and now look, 8.9 volts peak to peak. So a little bit less voltage because we don't have those big, that lower frequency pulling at it. All right, what I'm going to do is I'm going to turn on the power, and I'm going to get it so we can see a couple extra cycles, and then I'm going to change the frequency so we can just watch what's happening to the current and the voltage on our thing. But really, what we want, if I put the cursors up, all right guys, I moved this cursor where it's right at 28 volts. So see that line? That's really where we would want the voltage not to sag down any more than that, so that we don't affect that THD, right? So when it sags down below that, what we saw before is as long as we keep the voltage above 28, we don't really affect the THD. So we do have to probably take about half that ripple off. Okay, so let's just go ahead and look at it now. Turn it on. Okay, we're running. And let's get the cursor on a waveform we can see. Okay, so that's what it looks like. Okay, now I'm going to drop the frequency again. Okay, that's 5 kilohertz. We're back to 1 kilohertz, right? Okay, now watch what happens when we go below that. It's kind of interesting watching this. Okay, we're approaching 200 hertz. There's 200 hertz right there. Now, there's 120 hertz. That's okay. Okay, that's 120 hertz right there, guys. Now, look at that. Let's bring the trigger up so we're triggering, but isn't that crazy how the wave shape changes? Here, let me get a few more cycles so you can watch it. All right. Now look, we were at 500 milliamps. Let's look how high the peaks are now. So let's drop it. Now it's kind of changing because we're at the same frequency as the line frequency, but we're not. Here, let's look at the output voltage. See how the output voltage is kind of drifting? And what this purple waveform is the current charging our capacitors, our rectifiers, but we're not in sync. So now look how it's starting to clip here. Our 120 hertz from our generator is not synced up with our AC power coming in. So maybe it's going slightly faster. I don't know. Let's go down to 119. Or not even that much different, but no, that's worse. So here, maybe our AC power is slightly fast. Oh, it's pretty darn close. Okay, that's 120.06. Now we're pretty close to in sync with our AC power. Isn't that crazy? So we're getting a pulse of current the same time that our signal is going up. So it just happens to be that, the diode's putting out a lot of current right there. Okay. Now, here, let's actually go down in frequency. There's 100 hertz. Let's go to 60 because that's really our fundamental frequency of our power, right? Now, isn't that crazy? You get some kind of wild stuff going on. Let's trigger off of the, we'll trigger off our output voltage there. But look at that, how it's, again, we're almost in sync with our AC power. I'm slowly changing the frequency. I'm at 60 hertz, 0.02 right now. And we're almost synced up. 60.01. Look at that. So every other pulse, we get a big one, and then we barely get one in between because our frequency is slower. I mean, that's, you know, we're getting a lot of ripple current. Some pretty high peaks. Okay, I'm gonna go a little bit lower in frequency even. Let's go 20 hertz. Okay, there's our 20 hertz. Okay, there we go. Look at that. Look what it does. Whenever we get, you know, because we got 120 hertz basically coming in charge, right? Whenever we get a pulse that is where we're getting a big old, let's say a bass note, then we get a bunch of charge cycles. And in between, not very much. So I thought you might find that interesting. But you can see the drastic reduction in voltage, how it just pulls it right down. Okay, right there is about the worst case. I'm going to freeze it right up. Let's wait for it again. I'm going back and forth to the generator trying to get it in sync. Okay, I'm going to freeze that and turn off the power. It's probably taking a beating on our supply capacitors. So it's 1 amp per division, right? Look at that. We got 1, 2, 3, 4, 5, 6, you know, over 6 amp peaks. And then some of the cycles we barely get any current. And look at the voltage. There's a couple big waveforms in the middle of our 20 hertz right here that really pulls the voltage down. So that's the worst case scenario. That's why you end up needing some big bulk capacitors to keep that dropping. Because see, there's our line up here. Let me turn it blue again. See, that's our line right there, our 27 volts or our 28 volts. So I make it go yellow. That line right there, we don't want these blue ones or the purple ones dropping any lower than that. So you can see we have a big problem because right there we're dropping well below that. That is 5 volts per division. We got 5, 10, you know, it's like 13 volts lower than we want it during here. The good thing is it's narrow spikes. It's not big fat ones. Hey guys, what do you think of that? Pretty cool looking, right? I mean, I don't know if it's what you expected. And hey, before I go any further, I just want to thank my patrons. Really appreciate the patrons. I think that's super cool. You can become a patron for as low as $1 a month. Links are down below. And I want to thank everybody, all you guys for watching the videos and commenting and all that kind of stuff. Okay? Oh, and subscribe if you haven't done so, okay? I try to answer the subscribers first because I'm starting to fall behind. It's hard to keep up. Alright guys, so a little explanation if that doesn't make sense to you, or, you know, I mean, I wanted to show you the video first of this, you know, the scope, before I talk a lot. But, okay, so if you just want a little more explanation, now, if you think about it, you know, here in the States, our power frequency is 60 hertz. Okay, so once you go through a bridge rectifier, you double that. It's 120 hertz. So you're getting a pulse current, you know, because you're taking the negative pulses and you're putting them up on top. So you know, what used to be a negative, now it's a positive. So you get pulsating DC on the other side of the bridge rectifier at 120 hertz. Okay, so every 120 hertz, it's like, you know, you got these big old bulk capacitors, like a big old pool of water, right? And you got this big old bucket of water you're putting in every 120 hertz. Okay, now you're going to take out the same amount of water, you know, if you're the same power level, whether you're 20 kilohertz or 20 hertz. But now if you're 20 kilohertz, you're going to be going 20,000 times a second. So you can just use a little teacup, just pitch water out of the pool, okay? You know, and your mug starts getting bigger as the frequency starts getting lower, right? So when you're getting down to, say, 120 hertz, the same as what's coming in, now your bucket of water going out is the same size as the bucket that's going in, right? The average is going to be the same. Now what I did on this video is I synced up the generator with the power coming from the wall. So that was, so you could see what that looked, and then I put them out of sync so you could see how kind of funky that looked. Because imagine, you know, if somebody's putting a bucket in and you're putting a bucket out at the same time, their bucket of water could fall in your bucket at the same time you're tossing it. So the pool of water, the ripple, doesn't really change. It almost stays the same, if you notice that. And now if it's totally 180 out of sync, then, you know, then you're going to see it go up, and then you're going to see it go back down again when I take it out. So when it goes in, fills it up, and then I take a bucket out and it goes back down. So then you see almost a worst case scenario where you see a high peak and a low peak, you know. Well, then when you go down to 60 hertz, it even gets worse. Now you're only taking out 60 times a second. So if you sync it up, every other one of the pulses you're putting a bucket in, I'm taking twice that bucket out because I'm only doing it 60 times. So that way you get these big peaks. And then if we drop down to 30 or 20 hertz, now I'm even moving slower. So now my bucket has to be even, you know, like if it's 20 hertz, it's got to be what, 6 times bigger bucket. So I'm taking out a huge bucket of water and then you're dumping them in. So it's kind of the opposite as when I was at high frequency and I was taking little, you know, coffee mugs out. So yeah, it's pretty crazy. So, you know, that's the thing, is you have to look at your 20 hertz case, and you're going to get, yeah, you're going to get 3 buckets, you know, fill during that time, but you're going to get a huge bucket out at one time. So, yeah, the ripple gets kind of crazy. So, the next video, we're going to put some capacitors. I got some capacitors lined up here. We're going to try that and see how much capacitance we need to kind of smooth that off. All right, it's going to be pretty cool. We also have to solve the transformer, which one we go with. But yeah, we'll see if we can fit it both in. But I think we'll do at least the capacitor thing. All right. Okay. See you next time. Thanks.